Okay, this is the CAISO screen, California Independent System Operator. It's open for the general public to look at. Here's the web address up here. This is the power price. It's in 5-minute blocks. That is occurring right now on March 7th at 11:39. Every 5 minutes, the power prices change. So right now you can see that we have a minus $5 power. There's no congestion up here, 14-cent loss. So if you want to sell power and you don't have a contract, you'll have to pay $5 a megawatt to get rid of it. Down here in California, you can see that congestion. The price of power is 62 cents a megawatt. You have to take out the congestion, which means the lines are maximum capacity, so you have to pay to move your power. Somebody else won't be able to ship power. So the time you take congestion off and losses, it's a minus $5.31 a megawatt right now. I have seen it when it's minus $70 a megawatt up here in the northwest, and down here in the southwest it was about $1,500 a megawatt. So this is the 5-minute power price. Every 5 minutes these prices are going to change. Right now it's pretty much negative. This is the CAISO grid. It goes up into Canada, I believe, and it covers the whole west coast of the United States. This is one power grid. Countries broke up into 5 power grids, so if one goes down, just take the whole thing down. They have DC lines connecting it. So this is kind of unusual right now. Everything is negative in the blue. So if you're running a power plant and you don't have a fixed contract, and you just want to sell in the open market, you'd have to pay about $5 a megawatt to get rid of the power to keep running. This is kind of interesting, but anybody can go to this website. We'll go to the supply screen. Okay, the current demand right now in that area is 22,000 megawatts. The renewables is 21,000. There's about 15,000 megawatts in solar and 4,200 megawatts in wind. So here's kind of the renewable screen. Solar's about 74%, wind's 20%, geothermal's 3.5%. Right now it's mostly renewables. Here's the breakdown into what is feeding. So if you're running a natural gas plant right now, you're probably at minimum load, because it'd be cheaper to buy the power on the market than to run your plant. This is the demand. Current capacity is 43,000 megawatts. Current demand is 22,000 megawatts. The peak today is forecasted for 25,000 megawatts. So this is pretty interesting screens. They tell you quite a lot of information. If we go back to the price screen, we kind of call this the Skittle map. You have the day ahead price. This is important for a lot of the marketing people to buy and sell power on. There's different time frames you can buy and sell power. They have kind of a legend over here of what color's what. Usually in the mornings, it'll be high power. Then as the sun comes up, more solar prices will go negative for a while. Then in the evening, that prices take back off. You have to start running fossil fuels to make up the difference. But this is the CAISO grid area. We'll mention this when we deal with the power. California Independent System Operators, they will dictate what power plants run based on the price. You have to submit a bid, how much a megawatt you want to spend. Okay, this is our power plant, voltage and power factor control video. Also deals with power grid stabilization. I will throw a bunch of acronyms out. People should be aware of them. All these have websites. You can look any of these acronyms up. if you want to get information on them. They're public websites. There's a lot of information if you're interested. A lot of it's just a lot of technical jargon. Our CAISO website we looked at CAISO, California Independent System Operator. It showed a negative $5 a megawatt power. The power grid has usually two peaks. You have one in the morning and then one in the evening. During the middle of the day, power usage drops off, and at night it really drops off. So a lot of these plants have to swing twice a day pretty hard. There's 17,000 megawatts of solar. That's too much power for demand. So with a lot of wind and solar, it really makes running the grid difficult. Power plants have to swing a lot, especially wind. All of a sudden the wind stops and now you got to catch the load. And winter nights, you got to run these plants really hard because there is no wind or solar. You can see this plant right now, automatic generation control, AGC. We're not in it. If we were in it, the CAISO, the California group, would be running the plant. The merchant people send down basically a bid for how much we need per megawatt. And if it works in the schedule, they'll dispatch the plant. As you saw on our grid, we're looking at the 5-minute trend. Every 5 minutes, the price of power is jumping. There's day-ahead markets. Sometimes they'll buy a month out. There's different ways of purchasing power. Basically, the CAISO, they're a power marketing function. A whole bunch of utilities are part of it. That's why it's called the Independent System Operator. They operate a competitive energy market overseeing transmission planning. Companies buy and sell power before it is scheduled for delivery. The day-ahead market runs to clear bids, procure reserves, and manage congestion. Basically, the spot price of power is in 5-minute blocks. So if you trip a plant off, you could be in a lot of trouble if you have to go buy this on the spot market. I've seen times when it was minus 70 in Washington State and 1,500 down in Nevada, so you can take a hell of a hit on the plant operating costs if you trip off during really high powered time. BAO, the Balance Authority Operator, they requested we go down to 475 megawatts. So this plant, you just type in what you want. It's going to move 3 megawatts a minute down here. This plant's in the boiler follower mode with megawatt. Okay, there's our new target. We're going to go. We're using the turbine master to control the megawatt output. The boiler master is trying to maintain 2,400 pounds, so it follows the turbine. There's different control schemes you can run this, but this is usually the way that it runs the best. These are the different controls here. We can run it: boiler follower, turbine follower megawatt. Okay, as you can see, we're starting to drop. We're going to come down 3 megawatts a minute. The pulverizers are starting to back off. So right now we're running 105,000 pounds an hour per each pulverizer. Okay, this is the screen for the voltage control. The problem with power, it has to be consumed as it is produced, or you got to produce it as consumed. So for grid stability, you have to manage the megawatts, the voltage, and the frequency have to be controlled. The BAO, the Balancing Authority Operator, that's their job to deal with. The BAO, they're operating a transmission control area. They dispatch the lowest cost producers, balance between production and consumption, and meet reliability standards of NERC. Now, a lot of times you'll see some plants run, other ones get backed way off. It's just due to the price, like a natural gas or coal, or what it costs to run them. So these plants have to swing around quite a bit. Some of the terms that regulate what happens, you just can't randomly change VARs and change a plant. You have the NERC, NERC, North American Reliability Corporation, Nonprofit Reliability Standard. There is the FERC. It's a Federal Energy Regulatory Commission, that's FERC, government agency that regulates interstate electrical commerce. Then we have the WECC, WECC, Western Electricity Coordinating Council. That's what we're dealing with in the West Coast. They deal with protection, remediation, the AVR, Automatic Voltage Regulator, PSS, Power System Stabilizer, and the Western Interconnect. It has been approved by FERC, Regional Authority of Western Interconnect. So there's a lot of federal regulatory requirements. The NERC, NERC, has delegated some of its authority to create, monitor, enforce reliability standards to the WECC through a delegation agreement. So there's a lot of overlapping agencies that are trying to maintain a stable grid. There's also the RAS, Remedial Action Scheme. This is what runs all the breakers and relays and tripping. Automatic system that operates and corrects abnormal conditions in the electrical grid. It's a NERC standard. So this testing has to be done every year for tripping, the requirements. There's fines involved if you do not meet any of these. It's a lot of laws and rules. But like I say, if you are interested, you can look this up on the internet. As you can see, also I have like 7 unacknowledged alarms up on the screen. That's bad. You don't want to have this many unacknowledged alarms on your screen. We just did that for viewers. Okay, to control the grid system voltage, here's your voltage regulator. Have a transformer goes to a static exciter in this setup. We have a power system stabilizer. Also have a radio frequency monitor and condition monitor monitoring the generator. So to control the grid voltage, either you increase voltage, you produce VARs, or reduce load. The VARs are volts, amps, reactive. To decrease voltage, you have to consume VARs or increase load. To raise frequency, you have to raise generation output or cut load. To lower frequency, you have to cut generation output or increase load. The BAO is responsible for this. So as you can see right now, we have 545,000 volts on the line. That's way too high. The BAO wants us to drop that. The problem with high voltage, low frequency, it'll overflux the transformers. That's a number 24 relay that will trip the transformer. What happens is the maximum flux density exceeds what the core is capable of moving through the iron. So the flux goes through the steel core of the transformer, produces eddy currents, and produces a tremendous amount of heating, which you can destroy it. We have a reactivity capability curve. Right now, this is where we're at. I usually want to run a 0.95 power factor is about it. 60 pounds hydrogen pressure, it'll fall in this line. So different hydrogen pressures, you can run the generator different loads. It has to do with the cooling capacity of the generator. Down here, under exciting, you have to worry about step iron heating. It's basically kind of motorizing the generator. Over exciting, you have stator heating. So if we increase the voltage, we're going to over excite. It increases generator terminal voltage. It's called boosting. It causes the power factor to lag, which means the current lags the voltage. You'll heat up the generator core, we said. To lower the voltage, you'll under excite. That decreases generator terminal voltage. It's called bucking. Causes power factor to lead. Means the current leads the voltage. This will cause step iron heating. This is the stator ends that heat up. So there's different reactions for your power factor on your generator. Right now we're putting out 12,200 amps out of the generator. That power factor is like a +7. This is megavars, million volt amps reactive. So in order to drop the voltage, we're going to buck. Go back to the voltage regulator. Right now it's running in auto. It has to run in auto. Utilities must maintain voltage schedule and power factor band. Problems with the AVR or voltage regulator or PSS power system stabilizer last longer than 30 minutes. Have to notify your TOP transmission operator. Okay, I'm going to start dropping. Right now we're bucking. The transmission operator will notify the NERC. If you're out of compliance too long, there could be fines involved. Okay, you can see the voltage is starting to peel off. This happens if you lose a line. All of a sudden there's not as much load. The voltage picks up. Also on long lines there's a problem with this. Okay, we'll see what that does. Some problems with generators, you can have your shaft synchronous resonance. It's a low frequency harmonic resonance, imposes cyclic stresses on generator shaft. It can be a problem on a generator on a long line with switching that increases the line length. It's why we have the torsional stress relays. These are at a substation to try to minimize that. They've had generator shafts break from this phenomena. You won't see it showing up on the load. The generator shaft is twisting back and forth as it's getting hit with quick high loads and unloading and loading very fast. The power system stabilizer uses field voltage regulation of the AVR to dampen power and speed oscillations. The terminal modulates the terminal voltage 180 degrees out of phase with oscillations. Oscillations can be 0.1 to 1 hertz or up to 2 to 3 hertz. So the power grid, you can have some really weird phenomena. Okay, you see we're down to minus 105 megavars. You have to put the voltage regulator back in auto so we don't get nailed. I have seen people start up and leave this thing in manual, and you wonder why the VARs are going all over. We'll go back to our reactivity capability screen. Okay, we're right here now. We pulled down pretty good. In order to make a change like this, you'd have to be directed by the BAO, balance authority operator. Another interesting point. The exciter brushes right now are 227 volts. The exciter current is 3,000 amps. These brushes, they get inspected and changed weekly. You change these while the unit is running. There's limits to how many brushes you can change in a row and how many rows on each collector. You also buff the shaft. You have a piece of canvas on a board you'll buff this with. And I know sometimes they used to oak the shafts. Use a little bit of oak wood to, you want to maintain a special finish on this, the collector shaft. We'll clear these alarms. You should never have this many of them unacknowledged. That's just an operating tip. Anyhow, this is kind of a complex video. Anyhow, most of this stuff you can look up online if you're more interested. The CAL-ISO, CISO, that's pretty neat. They show you the price of power, how much is being produced, from where. There's a lot of good information on it, and it's open to the public. Anyhow, that concludes this video. Have a good day.